We have looked at kinetic energy and potential energy separately, and while they were good things to be able to cover in the sense of here is something new to calculate, it didn't really have any meaning. So now we're going to look at how to combine those ideas and what to do with them and how this can become a really useful thing. This is energy conservation. So energy conservation is exactly what it sounds like. We have this idea that energy can't be created or destroyed. We can just kind of rearrange it. So when we have a system, we can change the potential energy to kinetic and back, and those are completely okay, but we can't just get rid of energy. If you want to think ahead and start thinking about things like friction, it's not that those are getting rid of energy, they're taking it out of the system and putting it into a different system maybe. But we'll get to that when we get to it. For right now, energy conservation. So first I want to do a very, very simple case of this. Maybe I start with a ball that has a mass of 5 kilograms. I'm going to start with this thing being 2 meters off the ground, and it's going to start at rest. Maybe I want to know if this thing, when this thing gets to the ground, what speed will it have? So I want to find an impact speed. Now a while ago, we actually already found one way of solving this. If I said that my height down here was 0, I could set up my table, y initial, y final, v initial, v final, acceleration, and time. I can set up my table and say, 2 meters, 0, v initial is 0. I don't know this one, but I'd like to. My acceleration is from gravity, and I don't know my time. I would have my 3 equations that I would use, 1, 2, and 3. 3 would end up being the one I'd go with. V final squared is v initial squared 2a delta y, because this one doesn't have time in it. No time. So I would do that. I would find my v final squared v initial squared 2a delta y. This thing's going to be 0. So my v final works out to be the square root of 2a delta y. 2 times negative 10 meters per second squared. I'm going down by 2 meters. And I end up with the square root of 40, which is something like 6.3 meters per second. I do a little bit of thinking and assume that this thing is going to be moving downward, so negative 6.3 meters per second. I know how to solve this problem. I'm going to give you a different way of approaching the same problem. I can look at this, and if I say that's my final height of 0, I want to look instead at an initial position and a final position. I'm going to have potential energy, and I'm going to have kinetic energy. My initial potential energy is going to be mg h initial, and my final potential energy is going to be mg h final. My h final is 0, so that guy is 0. My initial kinetic energy, half m v initial squared. My final kinetic energy, half m v final squared. And my initial kinetic energy is 0. So then my total initial energy is going to be mg h initial plus 0. My final is going to be 0 plus half m v final squared. Now I've got mass in these equations. There's my mass of 5 kilograms, so I do know the mass, but when I did this before, I didn't care about the mass. So I'm hoping that the mass is going to cancel out. Let's see. my total energy of my system has to stay the same. I don't have friction or anything to take energy out of the system. So my total energy is going to stay the same, half m v final squared. There's m over here, those can cancel, which is nice. So now when I solve for v final, I'm going to multiply by 2. That gets rid of that. Got to do that over here too. And then I'm going to take a square root. So over here I'm going to get v final, and over here I'm going to get the square root of 2g h initial. I want you to look. 2a delta y under a square root, 2g h initial under a square root. I actually get the same, except that the sign on my acceleration is flipped and the sign on my height initial is flipped, but it works out to be the same thing. 2 times 10 meters per second squared times height initial, which was 2 meters. I again get the square root of 40, which is still 6.3 meters per second. If I want the velocity, I need to make sure to put a minus sign on there. I asked for an impact speed, and speed is just a scalar, so I just can keep the positive. All I'm doing with these is setting up a table. I'm saying my total initial energy is equal to my total final energy. I've already gone through how to find energies, potential, kinetic, and I'm just adding these things up. I can do this same thing, and that's great to have a new way of doing the same thing, but it doesn't add anything for me. The place that I really want to be able to use this is a situation like this. I've got this block. Let's stick with 5 kilograms. It's going to go down this hill, and let's give the hill an initial height of, we're going to stick with 2 meters. Now if I wanted to do this thing, and there's no friction, right? So let's say mu equals 0. I want to find the speed at the bottom. Now I run into some trouble if I want to do this with kinematics, because right here, yes, I could find the forces on this thing. Right? I can say here's my gravity, here's my normal force, something like that. And I can resolve those, get an acceleration. But when my block is here, here's my gravity, here is my normal force. When the block is here, here's my gravity, here's my normal force. So in these cases, I run into a major problem in that my acceleration's not constant. If my acceleration's not constant, then I can't use my kinematic equations. What I can do is use energy. So I'm going to say down here is still my h equals 0. When I set up my energy table, my initial potential energy is mgh initial. My initial kinetic energy, half mv initial squared, with v initial being 0. I'm going to start from rest. Sorry, I didn't mention that. My final potential energy, mgh final, 0. My final kinetic energy, half m v final squared. So I get mgh initial over here. I get half m v final squared over here. And when I plug that in, mgh initial equals half m v final squared. I can again cancel out my masses, and I'm going to get v final equals the square root of 2g h initial. And if you're really following along, to 10 meters per second squared, 2 meters, I actually still get 6.3 meters per second. I've dropped by the same amount. I started 2 meters up, I end down at the ground. I've dropped by the same amount. It turns out that I will have the same speed at the bottom, regardless of how I get there. So then the question, I suppose, would be, what is the disadvantage of using energy? It seems like this is covering everything that I was able to do before. Why didn't we just do this right from the start? Which is a fair question, but with energy considerations, we can't figure out anything about time. We can find, in this case, we found that whether we take this block and drop it from this height, or let it slide down here from this height, we're going to reach the same final speed. But if I have a couple of different tracks, if I have this track and I have this track and I have this track, if they're all reaching the same final speed or final height, they are all going to reach the same final speed. It's just this track is going to take a long time to get there because my block starts with almost no acceleration, takes forever to get to this point, and then it starts speeding up. If I take that same block and send it down this track, it's going to get to the bottom a whole lot faster. So I can't figure out anything about the time with energy. What I can figure out is just the kind of final end result. And sometimes that's all I'm worried about. So it's great in that regard. And sometimes I just need the information of what's going on in between. And when that's the case, energy is probably not going to be my approach.